Ionic bonds are one of the two types of bonds we're going to focus on. They're formed by the transfer of one or more electrons, so the key word is transfer. They're also called electrovalent bonds, which makes sense because the electrons in the valence sublevels are the electrons involved in the bonding. They form ions. When a metal loses an electron, it becomes a positively charged particle or ion. That's called a cation. When a nonmetal gains an electron, it becomes negatively charged, so it's an ion, and it's called an anion. The whole idea is that all atoms want to achieve a noble gas configuration, which is the S2p6 configuration, like the inert gases, which is column 8 on the periodic table. Now here's an example of an ionic attraction between two atoms. We have sodium solid and chlorine gas, and it becomes common table salt, which again is a solid. Both of these, by the way, are very dangerous. This is explosive and this is a deadly gas. But when you put them together, you get harmless table salts. This is the Bohr model. You can see that the kernel of the atom is everything but that blue electron. This is your valence electron. That's really all we're interested in when we're talking bonding. For chlorine, the kernel would include everything inside here and the nucleus. This is group 7, so it has 7 valence electrons. This is group 1, an alkali metal. It has 1 valence electron. This is a halogen. When they come together, initially they are both neutral, but their outer shell is not complete, so they're not stable. So what's going to happen is this metal wants to lose its electron to this nonmetal. And so you notice now sodium becomes positively charged. It lost an electron, where chlorine gained that electron. So chlorine becomes an anion, a negatively charged ion. This is a cation, a positively charged ion. Now what holds ionic compounds together? Electrostatic force. That's the positive and minus attraction. Something particular about the characteristic of ionic compounds is something called the cleavage. They all form what's called a crystal lattice, means they have a very specific structural shape, but then they have cleavage. If you look at the bottom diagram, this is calcium fluoride, an ionic crystal. You notice right there, there's a cleavage line. If you split it, it's got nice smooth edges on both sides. That's very characteristic of ionic compounds. Some other characteristics or properties, they have very high boiling points and melting points, meaning they're solids at room temperature. They do not conduct electricity when they're solids because there's no free moving ions. However, they do conduct when they're a liquid, or when they're vaporized, or when they're dissolved in water. We call that aqueous. When you form an ionic bond, it is always exothermic, which means it releases energy overall. It's actually endothermic to remove that first electron from the metal. That's the ionization energy, but it's very small. But then the nonmetal wants the electron so badly that it's still a downhill reaction. To form this, we use what's called electron configuration again from our previous units. If we use sodium and chlorine, you can see that, first of all, you remove the electron from sodium. That's through ionization energy, which is endothermic. It's going to cause a cation, positive sodium ion. Then you have the addition of the electron to the nonmetal, which is electronegativity or electron affinity. It really wants the electron. So it's going to be an anion, a negatively charged ion. And this is going to make the overall compound more stable than those elements being by themselves. And this is the same equation we saw before. Now here's the electron configuration. And we really don't need to worry about the electrons in energy level 1 here, or energy level 2. We really are only interested in the valence. Same thing here. We're not interested in energy level 1 or 2. We're interested in the valence, which is energy level 3, S and Ps. Really, it's that S electron that's going to be transferred over to here, this 3p electron, to fill that orbital. We can also draw the electron dot. 1 dot valence for sodium, alkali metal. And for chlorine, it's got S and Ps here. It has 7 dots. 2, 4, 6, 7. It needs 1 more to be complete, so it transfers right there. Sodium loses the electron, becomes positive. Chlorine gains that electron and becomes negatively charged. There's your electrostatic attraction.